When even a Nobel laureate in physics expresses doubt about our understanding of the universe, it is clear that we have entered a new astronomical era. However, Adam Rees is not alone in feeling uneasy. The James Webb Space Telescope is discovering more and more structures in space that defy traditional cosmology. How is it possible that galactic formations previously thought to be completely impossible are confirmed to exist? These spine-tingling findings raise questions about the future of our research and whether our previous theories have reached their limits. Seemingly simple questions now require complex answers. For example, consider the question of the expansion rate of the universe. Although this may seem straightforward at first glance, it touches on the core of a mystery that has perplexed experts for years. It is accepted that the universe has been continuously expanding since its origin approximately 13.8 billion years ago, which means that galaxies are moving away from each other at a rate proportional to their distance. In other words, if Galaxy A is twice as far from Earth as Galaxy B, then its receding rate is also twice as fast. Edwin Hubble, an American researcher, was a pioneer in identifying this correlation. To calculate the rate at which two galaxies are moving apart, it is necessary to know their distance and the constant that multiplies that distance, known as the Hubble constant. This is where things get a bit complicated. There has been considerable controversy among experts regarding the exact value of this constant. Previous measurements have yielded conflicting results, suggesting that the value depends on the measurement method used. One method for measuring the expansion of the universe is based on the cosmic microwave background radiation, a nearly isotropic fingerprint of the early universe that serves as strong evidence for the Big Bang theory. Calculating the expansion rate using this radiation yields a value of approximately 60 km per second per megaparsec. For context, 1 megaparsec is equivalent to 3.26 million light-years, and 1 light-year represents about 9.4 trillion kilometers. On the other hand, if we measure distances in space using so-called Cepheid variables, a type of star that exhibits periodic fluctuations in brightness, the expansion rate rises to 73 km per second per megaparsec. This suggests that the universe is expanding faster in our visible range, up to around 3 billion light-years, compared to the total expansion. This discrepancy between the two values is known as the Hubble tension, and so far, no researcher has been able to explain this unexpected variation. The James Webb Space Telescope has turned its attention to this enigma. Some scientists previously speculated that the mystery surrounding the expansion rate might be due to a measurement error from the Hubble Space Telescope. Adam Rees was also interested in determining whether there were errors in the Hubble data. This physicist from Johns Hopkins University, who received the Nobel Prize in Physics in 2011, along with other researchers, demonstrated that the expansion of the universe is accelerating. Rees and his team used the James Webb Telescope to investigate the cause of this discrepancy in the Hubble expansion data and to look for possible measurement errors. To understand how the expansion of the cosmos is determined, scientists use the so-called cosmic distance ladder. Each stage of this ladder builds upon the previous one, meaning that any possible error in one measurement can affect all subsequent stages. However, the methods mentioned above prove to be reliable only to a certain extent. This is because, as the distance increases, it becomes more challenging to measure accurately. The reason is that the light from distant stars mixes with light from other stars, making observation difficult. Nonetheless, the James Webb Telescope is 100 times more powerful than the Hubble telescope, allowing experts to peer farther and with greater detail than ever before, delving into the farthest secrets of the universe. In a study published in the astrophysical journal Letters Asterisk, a rather revealing picture emerged. The James Webb Space Telescope scanned the entire area previously observed by Hubble and found no errors in those measurements. Therefore, the Hubble tension problem persists. Adam Rees offers a brief but profound explanation. It could be that we have simply misinterpreted the nature of the universe. We must now investigate whether we have missed something in our previous investigations and explore how to connect the origin of the cosmos with its present state. Solving this mystery could put Einstein's theory of gravity to the test. However, researchers working with Rees are not the only ones tackling the confounding Hubble tension. Scientists at the University of Bonn and St. Andrews are also exploring this mystery and have proposed a new possible explanation. They hypothesize that our planet lies in a bubble-shaped region of space with relatively low matter density. The density of matter is highest near the edge of this bubble, and gravitational forces from that dense matter pull galaxies towards the bubble's boundary. As a result, these galaxies appear to be moving away from us faster than expected. While plausible, this explanation introduces a new research dilemma. Why doesn't the standard model predict the existence of such bubbles? According to the model, matter should be uniformly distributed across space. The standard model is based on Albert Einstein's theory of gravity, but what if gravitational forces behave differently than Einstein predicted? For this reason, scientists have considered a modified theory of gravity proposed by Israeli physicist Mordechai Milgram in the 1980s. However, Milgram's modified Newtonian dynamics, MOND, has yet to gain full acceptance, despite its accurate prediction of the existence of such bubbles. If gravity indeed behaves according to MOND, then the entire debate surrounding Hubble tension could potentially be resolved. In this new context, there would be only one constant for the universe's expansion, and observed discrepancies would result from irregularities in matter distribution. Time will tell how well this approach is accepted and confirmed, but a review of the cosmic past reveals just how much remains to be understood about the universe's future. Sometimes, a single piece of information can astonish even the most experienced astronomers. For example, the record redshift of the galaxy Jade's GSZ 1440 indicates that this gravitationally bound group of stars already existed 290 million years after the Big Bang. The existence of this ancient galaxy raises intriguing questions. How could it have been so bright and massive at that early time, and where did the necessary matter come from? Thanks to the James Webb Telescope's near-infrared camera, NIRCam, scientists discovered that this structure likely took around 100 million years to reach its current size. This infant galaxy defies virtually all theoretical models and computer simulations of the early cosmos. In fact, Jade's GSZ 1440 is in good company. 6 galaxies that the James Webb Telescope added to star maps in early 2023 also turned out to be much more massive than expected. These galaxies, formed when the universe was only 500 to 700 million years old, resemble today's Milky Way. Since this seems impossible according to conventional cosmology, experts have nicknamed these galaxies universe breakers. In contrast to the expected baby galaxies, researchers observed impressive objects with more than 10 billion solar masses of stars. One of them may even contain over 100 billion solar masses. The question now is, how is this possible? If any of these massive galaxies is confirmed, it could stretch our understanding of cosmology to its limits. To explain their existence, the density of matter in the early cosmos would need to have been up to 5 times greater than current models suggest. Alternatively, these galaxies may have developed through mechanisms we do not yet understand. These findings signal the need to rewrite the history of the universe, and possibly the Big Bang theory itself. If you enjoyed this exploration of cosmic mysteries, please hit the like button, subscribe, and leave your thoughts in the comments below. Thank you so much for watching, and I'll see you in the next video.